for a year. Then he moved to Lemoyne College in Syracuse as a visiting professor. And shortly thereafter, he took now a tenured track job at CUNY, Manhattan Community College, where he's been for 3 or 4 years. So he's moved from upstate New York to now hit the big time in the Big Apple.
Right.
Congratulations
From the middle
to
of
you.
nowhere to...
Yeah. So, okay, so today he's going to talk about some interesting work he's done on gravitational lensing and understanding how you can use gravitational lensing to probe properties of dark matter subhalos.
Thanks, Louis, for the intro, and thanks for inviting me. It's great to be here. So I want to talk about how we can use gravitational lenses to probe dark matter substructure. And first, I want to motivate why do we want to do that? So the standard cosmology that we generally use today is that about roughly 25% of the energy budget of the universe is what we call collisionless cold dark matter. So this is, the stereotypical model is that it's a massive, weakly interacting particle, collisionless. So they only interact via gravity, don't interact via light at all. And then most of the rest of the budget is dark energy, which we won't get into here. But that's the paradigm, and it's worked very, very well on large scales. Right, so when we test this model against observations of galaxy clusters, the abundance of galaxy clusters, X-ray clusters, same idea, gravitational lensing, weak lensing over large scales, and also baryon acoustic oscillation surveys. All of that seems to match pretty well with lambda CDM. There's a little bit of tension, for example, in the Hubble constant, but by and large, it works very, very well. If you go to small scales, that's what things get weird. I think it's fair to say that on small scales, CDM has kind of been under siege for quite some time, and every time we think the siege is broken, new problems just keep cropping up. So I want to tell you about one of the big problems that's relevant for what I'm doing, and that's what we call the missing dwarf problem, CDM. This problem has had many incarnations, and I want to describe the most recent. By the way, please feel free to interrupt me if you have questions at any point. I prefer to keep it interactive if I can, so let me know. Yeah, don't mind being interrupted. Anyway, so one way to describe the missing dwarf problem is as follows. Suppose you measure for a given galaxy, well, first of all, starting in simulation. So if you do a dark matter simulation, and you say for each galaxy, what's the fastest velocity of a dark matter particle? We call it maximum circular velocity. That maximum circular velocity usually happens at a characteristic radius, and therefore depends on sort of not the total mass of this galaxy, but sort of the central density within a certain radius, right? And then we can say, okay, how many galaxies do we see with Vmax of 10 kilometers per second, 20, 50, etc. So we plot basically abundance of galaxies at a given Vmax, and this is the theoretical prediction from cold dark matter simulations, right? Well, now we can go and say, let's measure this for actual galaxies. So the ideal way to do this is to use H1, neutral hydrogen, 21 centimeter surveys. That H1 disks go out farther than the stars do, typically. And so we try to get rotation curves for these H1. Some of them are resolved rotation curves, many of them are not. But when you plot the abundance, so you have to sort of infer what is Vmax given this rotation curve. So you plot that abundance, and this is what you end up getting. This paper came out, I think, just a few months ago. Julia Gomez et al. Once you get below like 100 kilometers per second, that's where you see that we're really getting a lot fewer galaxies than we expected. And this problem has come up, before in many contexts, the missing satellites problem, for example. But this is it's a nice simple way to state it. So what does it mean? How do we explain this, right? There's a few ways you could explain it. Maybe galaxy formation is being suppressed for, below Vmax of, say, 100 or 80 kilometers a second. We expect that to happen to some extent, right? So stellar feedback, the UV background of ionization would photoevaporate gas. So if you're in a really low mass halo, you might evaporate that gas. It might escape before you form any stars, right? So maybe we just don't see most of the galaxies that are at this low Vmax. They don't have stars, or they're just very, very faint, right? So that's one factor. Another possibility is that maybe just the dwarfs inhabit lower density halos than we thought, right? So that the galaxies that we thought were here, for example, something lowered their density and moved them out to a lower Vmax. See what I mean? So you kind of shift everything down to some extent. And it's true, indeed, when we look at satellites of the Milky Way, they do seem to have lower essential densities than we expected from the simulations. So we call that the too big to fail problem, right? So one way that this can happen is when star formation starts up, supernova eject a lot of gas, and that tends to sort of puff up the dark matter. It kind of responds by spreading out a bit. Supernova feedback. So that's, again, another option. So the question is, and finally one last factor is maybe just the velocities we're measuring are much smaller than Vmax.
What's happening in theory? Because when the theory takes off from the observations, there's sort of a kink in the slope.
Right.
Yeah. Is there anything you know is anything special happening in theory there, or just comes out of theory?
Right. That's a good question. I'm
Okay.
not entirely sure. Yeah.
Is this for satellites or central? Is this for like all halos that have
All
Vmax, or
halos.
this is for all halos? Okay.
Yeah, and I think here we're really just looking at field halos.
So you're just looking at field halos.
Yeah. Do you happen to know? I'm not quite sure what.
It might be they combine. Well, if they combine satellites and field halos, that might make a sense why there's a bit of a jump there.
Yeah, that could be. It's also true that once you get above 100, then the baryons, right, the stars and the gas, do contribute significantly to the rotation curves. But once you get down below like 100, I think you can start to ignore the stars and gas.
So if they ignore them all at once,
Yeah.
it might be a kink or something.
Something like, yeah. So
Yeah.
maybe it has something to do with that. I'm not quite sure. So yeah, all of these are possibilities. So the question is, do these explain? And the jury is still out, but it seems like it's not quite enough. Here's the reason why we think it's not quite enough. There's a couple constraints on star formation that you have to take into account. And one thing is the fact that you have, there's an empirical relationship between your Vmax, or your circular velocity, and how much baryons you have, the mass of your stars and gas. We call that the Tully-Fisher relation, baryonic Tully-Fisher relation. And any simulation that puts in star formation, we gotta match that, right? If we have too much feedback, we get rid of too much gas, right? And then it wouldn't match that. So that's one constraint. Another constraint is that if you have so much feedback that your disks come out very small, then they might not match the disk sizes we see and the rotation curves that we see. I haven't seen a solution yet that actually matches the rotation curves that we see, the resolved rotation curves we see. So at this point, it still doesn't seem to be something you can solve with just feedback. And even if we can solve it with feedback, the question is, does it solve it, right? If you tune the parameters so that star formation solves these issues, well, we've shown that it is a solution. We don't know if it's the solution, right? So that's the debate. I mean, it's kind of an impassioned debate on all sides. So, okay, if it's not star formation, what's going on here? Well, another option is that maybe small dark matter subhalos just don't exist, right? And that does happen in some dark matter theories. For example, warm dark matter, where you get dark matter particles that were relativistic early on in the stages of galaxy formation. And those particles could just escape from small clumps of matter, and you don't get any small dwarf galaxies. So that's one option to at least to get rid of the low mass halos. Although it is heavily constrained by lack of alpha force data now. Still debatable if it would work. Now another option is maybe that the dark matter halos had low density cores to begin with. There's a couple of ways to achieve that. One is if you make the dark matter interact, if they have self-interactions on some scale, right? Then those interactions can actually transfer heat into the centers of halos. So those cold particles that settled in the center of the halos, right? They get heat gets transferred through these interactions, and then they kind of get driven out. So that gives you a core in the middle of these things. That's one way to do it. Another way to do it is with this so-called fuzzy dark matter. This is a more recent idea. The idea is that if the dark matter particle is extremely light, and if it's boson, then they can have a de Broglie wavelength that's actually galaxy-sized, right? And then the uncertainty principle actually comes into play. It says you can't pack too many particles in the center. So instead of having a cusp in the middle, you end up with a core. So that the sort of canonical model for that is an axion, which is an extension to the standard model. So these are all ways to sort of alleviate this missing dwarf problem. Now, one last thing I should mention, although it's not really important for this talk, it's also possible that the perturbations that gave rise to these galaxies were suppressed during inflation, right? We think that inflation generated the perturbations. It could be that inflation physics actually suppresses small-scale perturbations. So that's something I've looked into with the budget in the past. So, as a theorist, I'm interested in testing these different dark matter models. And another big, I think, driving factor is that we've been searching for the WIMP, a weakly interacting massive particle, for 2 decades, I guess. And we haven't found it yet, at least not conclusively. There's still parameter space left to explore, right? But, having not found the WIMP, people are getting more interested in possibly other models that are not just cold dark matter. And I think these other dark matter models, they have intrinsic particle physics motivations, right? The sterile neutrino is a warm dark matter candidate. That was an extension to the standard model, right? To give neutrinos mass. There are plenty of other, the axion, for example, could give you the fuzzy dark matter, also well-motivated extensions. So they're interesting in their own right, I guess is what I'm trying to say. So to sort of test, to distinguish between these different dark matter models, I want to be able to look at really low mass dark matter halos, subhalos, that have almost no stars or gas, right? I want to look at the halos where, very little, where star formation couldn't have affected their abundance or their density and so forth. So how do we look at the dark guys? Gravitational lensing is one of the most promising ways to do this. So gravitational lens, you probably all have heard of this. In a gravitational lens, basically you have a distant galaxy and then a distant light source well behind it. And we're talking billions of light years away, cosmological scales. And the light from this distant source, it could be a galaxy, it could be the quasar in the galaxy. That light gets bent by the gravity of the intervening galaxy. If the bending is strong enough, you can get multiple paths that form an image. If it's very symmetric, it gets smeared into a ring. If it's less symmetric, it forms 2 images. If it's much less symmetric, you can get 4 images, right? So this being an example of the quad lens, 4-image lens. First discovered in 1979, now we've cataloged over 400 of them with pretty high confidence. We expect tens of thousands of more from the Euclid space mission, LSST, and so on. We're going to have a lot of lenses. It's going to be a huge data set, right? And we want to be able to mine that to understand, well, many things, among them dark matter structure. So how does subhalos, dark matter substructure, how do they affect a gravitational lens? If you have quasars, then you can imagine if I put a subhalo, a dark matter subhalo, near one of the images, it can affect the magnification of that image, so one of them will appear brighter than you would expect. It can also affect the arrival time of that image. It will arrive earlier or later than you expect. And there's been some work on this using radio quasars to try to look for substructure. But it's still, there's not a huge number of lens quasars that work for this yet. I think there's only 7 or 8 so far. But it'll become a bigger deal with LSST. I think more promising right now is when you have resolved lenses. Right? When you have a resolved images in a gravitational lens, then dark matter substructure introduces distortions in those images. Kind of like, when you're looking through a window, raindrops on the window pane distort the image that you're seeing. This is actually a photograph, by the way. To me, it looks like Van Gogh or something. It's a pretty cool photo. But yeah, so you can imagine if I want to figure out, okay, where are the raindrops and how big are they, etc. You can get that from studying these distortions, right? That's what we're trying to do with gravitational lensing. For dark matter subhalos, those distortions are milli-arcsecond scale. The biggest subhalos might be tens of milli-arcseconds compared to the scale of the lens, which is typically an arcsecond, right? So that sometimes they call it milli-lensing as opposed to macro or micro lensing. So very small distortions. Okay, so there's one complication to this that is very important to understand, and that is gravitational lensing conserves the surface brightness of an object, right? So for example, if I have an object that has a totally uniform surface brightness, and I put a subhalo in front of it, right? The lensing doesn't do much because it can't actually change that surface brightness. All it can do is sort of distort where each point gets lensed to. Might magnify it a little bit, but it's not. You're not going to be able to tell that it's really substructure. By the way, the scale here is kind of arbitrary, but for a subhalo, this would be like milliarc seconds again. So this isn't going to help us much. We need an object that's lumpy, right? We need an object that has surface brightness variations. And so if I put, for example, two blobs, they might be star-forming regions, and you put a subhalo in front of it, now you're going to see that distortion, right? This is what we're looking for. And now, if you just have one image, that's not really a smoking gun. You might say, well, maybe these blobs just look weird, right? Like, maybe they just have these kind of odd distorted shapes. But if you have a lens with 4 images, or at least one other image, I can compare to the other images and say, well, the other images don't have this perturbation, but I see it here. That tells you there's substructure. That makes sense. So what kind of targets are going to help us do this? Again, we need milliarc second resolution. And we need surface brightness variations on that same scale. So a good target for this is sub-millimeter galaxies. When you look at a sub-millimeter galaxy, these are very dusty star-forming galaxies. And the star formation happens in these little globs, these little pockets, where you're seeing molecular lines from that dust. So the sub-millimeter galaxies, they look very messy. They have a lot of structure. And this is, for example, a lensed sub-millimeter galaxy. There's actually 4 images, 1, 2, 3, 4, although they get sort of blended together. But you can see there's little pockets of star formation, and that detail allows us to look for subhalos. So this is an ALMA image. It's a spectacular, their first high-resolution image of a sub-millimeter lens. So these are great targets. I know ALMA it's presently it's observing several more targets of this type.
So you always have perfect alignment for that one, right? Do I interpret that, or is
Perfect.
you always have perfect alignment between the lines and the
Almost, yeah. If it was perfect, it would be like a nice Einstein ring. But it's asymmetric enough that we get these 4 kind of separate images. So, yeah.
I actually cross-correlate the 4 images and really get the orientation target, identify the blocks.
Exactly. Yeah. So if I see, for example, that there's a weird perturbation here that I don't see in the other copies, right? The other images, then I can say there's substructure there. So that's the idea. So sub-millimeter galaxies are good. Also, Lyman alpha emitters, lens Lyman alpha emitters also have a lot of structure in them. Those are typically star-forming galaxies that have a lot less dust than sub-millimeter galaxies. And so again, you're seeing pockets of star formation where Lyman alpha is being emitted from those regions. The first HST images of these Lyman alpha emitting lenses that just came out just a couple months ago. These are like hot off the press. And as you can see, they have a lot of structure in them. They have not been, there's no substructure analysis of them yet. And I'm very excited about this one. I'm hoping we can get our hands on some examples of this. Again, very promising targets. So they're called, by the way, this particular site is called Bell's Gallery. I think it's BOSS, I forget what the rest stands for. Something BOSS, Galaxy, Lyman Alpha, but they're coming from the BOSS survey, which uses SDSS3. Finally, nobody's actually done this yet, but quasar jets could be observed with VLBI, for example, using the square kilometer array, which is a huge radio telescope array coming up. That could see even smaller structures, sub-milli-arcsecond. By the way, I should say, the first two in this category, it seems that we can detect subhalos down to 10 to the 8 solar mass, maybe 10 to the 7 solar mass subhalos. So you're really getting down into subhalos that might have no stars or gas at all, right? Quasar jets could conceivably get down to like 10 to the 6 or 10 to the 5 solar mass, which is an exciting prospect. Okay, so have we actually detected these things yet? We have. There's been 3 detections so far of subhalos. 2 of them have been in HST lenses. One of them is in the lens I just showed you, what we call STP-81, the sub-millimeter lens, using ALMA. This is a representation of where they found the subhalo. So this is sort of tracing the lensing mass. Got a subhalo right there. So when I got into trying to understand these things, I was worried about what can we really say about these subhalos? Can we measure, how massive are they? Can we say anything about how dense are they?
What's the mass ratio between those?
Between the host and the subhalo? Oh, it's quite large. I mean, the host galaxy is a giant elliptical. It's an early type. The mass of the subhalo, they're getting about 10 to the 9 solar masses.
These are like 13 to 9.
Yeah, 13 to 9. So it's pretty substantial. So my main concern is we need reliable mass measurements to really, if we're going to compare to dark matter simulations and test cold dark matter, we need to say with certainty what is the mass of this subhalo, some measure of its mass. So just to give you a quick sense of what the subhalo might do in a lens like this.
Sorry, please.
Oh.
So I have some familiarity with this. So one of the things I've always been concerned about is that you assume you understand what the source looks like.
Right.
And you know that sub-millimeter galaxies are massive, right?
Right.
Yeah. Okay. So how can you then disentangle the degeneracy between structure and your source versus the actual
Right.
lensing?
Right, so yeah, I mean, some people do kind of parameterize the sources and try to fit like analytic profiles. I worry about that because like you said, they're very messy.
No, I mean, we still don't even know if sub-millimeter galaxies are dominated by mergers.
Right.
There's camps that say they are, there's camps that say they aren't. I mean, it could just be that you're seeing a sub-millimeter part that happened in Dustius and similar galaxy. So the information that you're extracting, you're right, if you knew what the source looked like, it would be easy.
Right. Right.
But the substructure you're trying to probe on these dark matter halos is comparable, if
Right.
not smaller, than
Yeah.
the uncertainty of the source itself. So how do you guys get around that? Do you just kind of like,
No, we don't do that. No, so what, and I'll show you in a minute sort of how I do the analysis, but basically we pixelate the source. So we assume some pixelation, and then we do an inversion to sort of recover what we think the
this is a
source.
non-parametric.
Yeah, exactly, non-parametric. Now, if there was only one lensed image, then you're right, it would be hopeless. Because we don't know what the source should look like. But because we have, in this case, 4 copies of the same image, that helps us a lot. Right? Because we can compare the different copies. So that's kind of the idea.
You're presuming that the dark matter, the lens itself doesn't have a substructure, right?
No, that's sort of what we're modeling.
Sorry, that isn't contaminating the actual light that you're getting, right? So you're assuming
Right.
the light that you're measuring is arcs and rings is only from the source.
Right.
You don't know if the lens
Well,
itself.
we could say that, I think, with good confidence, because the host galaxy, it's an early type galaxy,
And
totally
these days,
invisible. Yeah, totally invisible in submillimeter. That's one nice thing about submillimeter is you don't even see the host basically.
Have you ever seen a dusty elliptical galaxy before?
Yeah, not yet in these lenses. I mean, yeah, I could see that being an issue down the road.
I mean, these lenses tend to be higher redshift, right? So that's where the people's recognition comes from. Anyway, so
Yeah.
these are just, I know these are sort of nagging details, but it does whenever, I think these are quite impressive, don't get me wrong. This is absolutely the right way to go. But one thing I've always been concerned about is when you're trying to disentangle all of these competing effects to actually recover a true signal.
Yeah, no, it's complicated, definitely. But yeah, so just to give you a sense of what a subhalo would do here, I've sort of simulated here two star forming regions that are kind of like SDP81, two bright star forming regions. One of them, by the way, there's only 2 copies. 1, 2. The other star forming region, there's 4 copies. 1, 2, 3, 4. That's right. Now this black curve is what we call the critical curve of the lens. Anywhere near the critical curve, the magnification gets very large, right? If I put a subhalo, say, out here, you're not going to notice it much. But if I put it very close to the critical curve, the effect gets highly magnified. So, for example, I put a subhalo right here, and I'm simulating a 10 to the 9 solar mass subhalo, like what they found. You notice it warps the critical curve pretty dramatically. And you also get not only distortion of the images, actually, I think a couple of little tiny images that crop up. Very hard to resolve. So it's a dramatic perturbation if the subhalo is large enough. So what people have done until now is they say, okay, I'm going to include a subhalo in my model. And usually they just assume it has an isothermal profile. It just goes like 1/r squared. Why do they assume that? Because it's easy. Because people, in lensing, people are always using isothermal profiles for everything. It's just what we're used to. But there's no real good reason to expect that it should be isothermal. If you believe the simulations, it might be NFW, right? So I was worried about that. I was saying, okay, well, what if it's not isothermal? I'm modeling it that way, right? So I wanted to look at what if, what's the bias in the mass that we get by using the wrong density profile? So that's one problem that I was worried about. The other problem I was worried about is that we don't really know how close this subhalo is to the lensing, to the plane of the lens, right? It could be in the lens plane, or it could be much further out. The reason that matters is because the tidal radius of this subhalo depends a lot on how close it is to the host, right? So just to give you a sense of scale here, this subhalo, the projected distance to the host is 6 kpc, right? This is a giant, giant elliptical galaxy. 6 kpc is very, very close. If you assume that it was in the lens plane, it would be severely tidally stripped. And that's the assumption that the lens modelers have mainly made. It's more likely to be further out if you believe the simulations in galaxy counts. It might not even be a subhalo. It might be some intervening halo on the way to the lens, right? It could be something along our line of sight that's not actually a subhalo. So this is the kind of thing I wanted to look at. How biased is the mass that we get because of this assumption, right? If the subhalo is farther out. So I want to, how does the perturbation from the subhalo differ if you change these things, tidal radius and density profile? So getting back to what you were asking, to actually test these things, I need to be able to model pixelated images of lenses. There's some software out there to do this, but I decided to take the easy route and code everything up from scratch and take an entire year to do it. And so I created what I call a QLens. So QLens is it's a parallel lens modeling code. I made it extremely parallel so it could handle these intensive calculations. I'm going to try and make it, my plan is to make it public by the end of the year and open source. We're starting to develop Python bindings, or well, we're getting a student to start developing Python bindings, which I'm very excited about, to make it much more versatile. So by the way, if you're interested in getting into lensing or getting a student into lensing, let me know. I'm happy to share it. I've tried to make it very user-friendly, easy for students to just get started on it. It can model point sources like quasar lenses, as well as pixelated ones. And it can do MCMC, Bayesian analyses, nested sampling, or minimization. So with pixelated images, what we're doing is taking this image and doing a linear inversion to recover a pixelated image of the source. And it's, it's a complicated thing. You have to factor in the point spread function, all with that. You also have to set a prior on how smooth your solution is. Otherwise, it just tries to fit noise. Right, so you put in what we call regularization to smooth the solution, and we optimize that on the way. So using this code, I looked at a few test cases. I said, okay, what if I take this lens, the SDP81 lens, and first I'll just try a subhalo that's isothermal, which is what everybody assumed. So here's the perturbation you get. Then I said, what if I make the slope shallower? So instead of r to the minus 2, it's going like r to the minus 1.5, or even shallower, r to the minus 1, which is more like an NFW, bigger part of an NFW. And you can see that the structure of the critical curve is quite different. Now, it's a little bit subtle, in terms of the surface brightness, but you stare at it long enough, you start to notice differences in the perturbation. Further out, it's a little different, as well as close in. The last case I tried was, what if I take a subhalo isothermal, but now I'm going to put it 100 kpc away from the host. So this is, further out along your line of sight, which means there's less tidal stripping. It has more mass, right? And you get a solution, again, which stare at it long enough, you start to see differences further out. So what we want to know is, okay, it looks like we're getting different perturbations. Can I measure the mass in a robust sort of way? And we noticed something very interesting, which is that if you look at the distance from the subhalo to the critical curve, where it's warped the most, it turns out that distance only depends on the mass of the subhalo enclosed. It doesn't depend on how that mass is distributed. So no matter what the density profile, right, this is set by how much mass is there. And we showed that analytically, and then we went and showed that using the lens modeling, that that's the case. So in other words, when I plotted each of these things, what I didn't tell you is that I normalized the subhalo so that that same 10 to the 9 solar mass is inside the critical curve. So that gives you the same distance to the critical curve, what we call the perturbation radius of the subhalo. So this could be an unbiased estimator, right, of how much mass is in this thing.
Does that depend on the geometry of the source or no?
that displacement state?
Not at all. Yeah, totally independent of the source. This is just how it works in the visual proof. Okay, so we modeled each of these lenses the same way that people have been doing. We modeled it with an isothermal profile. And then we plotted the mass profile of the subhalo. So what I'm plotting here, this is a scaled mass, but I actually gave a mass scale to the right here to orient you. With respect to a radius from the subhalo. And in the case of the subhalo that we put far away, at 100 kbc, if you get out far enough to look at what's the total mass inside the subhalo, the mass you get from the fit, which is this dashed line, severely underestimates the actual total mass, which is the solid line. Really by almost an order of magnitude, right? That's pretty dangerous, right? So you might think it's a almost 10 to the 9, 10 to the 10 solar mass subhalo, might actually be like 20% that, or 10% that. However, we looked at what's the mass inside this perturbation radius I just told you about, and that's where the dashed vertical line is. And compared the two at that radius, I found they're pretty close. They're to within a few percent of each other. So that was pretty encouraging. That means we found kind of a robust mass estimate from this. Same thing turned out to be true for each of the other examples. Again, within this perturbation radius, we were getting the right mass. So this is for the shallow slope case. Total mass is not so biased in this case. By the way, I should mention, so why did we get the total mass so wrong? It's because we modeled it with a subhalo that we assumed was much closer to the host galaxy. So we assumed that it was very close and was very tightly stripped, right? So that's why our total mass was coming out much smaller, because we overestimated the tidal stripping of this subhalo, if that makes sense.
No, that doesn't actually make any sense at all. I mean, you have to make, you're doing some model, and you have to assign some mass to what you're calling the subhalo.
Right.
Okay.
Well,
so you know, you're setting up a model based on something you already know you set up in the computer.
Right.
And then you're seeing what models get close to that. So I
Right.
don't understand.
Yeah.
What do you mean by, how does tidal stripping come into this at all? Isn't it just a mass assumption about the
Yeah, no, so it's not,
secondary perturbator?
right, so the mass itself, that's not like one of our parameters. What we're doing is fitting a density profile to the subhalo.
So it's a truncation radius or something like that? For
Exactly.
the density profile?
Yeah, there's a tidal truncation radius, so, you know, there's something that normalizes it, the mass profile.
But it's you've got a profile and you just decide to stop it at some radius.
That's what people have been doing.
Okay.
Yeah, and we don't
Just
really know
stop- I mean,
what
I don't- you know,
radius, right?
I don't know that I would call that a tidal stripping radius. There's no physics in that. You just choose a radius.
Well, I mean, yeah, we call it the tidal truncation radius, but yeah, we're not modeling the physics of that.
But I think that your point, that's what has been done in the lensing world.
Exactly.
To assume that sort of nonsense.
Right.
Yeah, so really they're just using the Jacobi radius is the idea. So yeah, that was a major systematic. And what we're saying is you can overcome that if you use a different, you know, this subhalo perturbation radius. So finally, this is no surprise, but if you model, if the subhalo is actually isothermal and it's in the lens plane, and we model it with that same model, then we do reproduce the entire mass profile very well. So that the fit and the actual subhalo profile are like spot on. Which is a nice sanity check. Make sure we're doing things right. Okay, so to sum up here, we're finding that the masses of subhalos in these strong lenses, you can constrain them within a characteristic radius. We call it the effective lensing mass. You can't constrain the total mass well because of these systematics that I talked about. But you can use this affecting lensing mass to sort of compare to dark matter simulations once we discover enough of these things, right? We might be able to do better if we can actually constrain the tidal radius or the density profile of the subhalo directly. And that's something I'm working on right now. I think we can only do it with the biggest subhalos. But that's also an exciting possibility, is to actually look for, what's the inner slope, is there a core, and so on. So yeah, that's the talk.
So if you invert this problem, and people have done many times, and try to use various assumptions about what the dark matter distributions look like. Oftentimes you can see the galaxies in the lenses as well as the background, for simple ones like QSOs.
Right.
And you try to use the observations of the lensing to probe cosmology parameters. You get answers that are way, way wrong.
Right.
At least wrong compared to what we expect them to be.
Right.
So what gives you confidence that you can then assume a cosmology, turn around and get the right answer for anything else?
Well, I mean, we're not, certainly for, the subhalo detection I'm talking about, we're really, I would say that we're in the really early stages of being able to do that. I mean, with only 3 subhalos, right, it's pretty hard to be able to do that. But, once we detect 10, 20 subhalos, we can try to compare to the mass function, right, that you get from simulations.
So you're saying like in strong lensing measurements, the cosmology is a bit wrong?
It's always wrong.
It's always wrong. Yeah.
Kachanik did this
yeah.
10, 15 years ago, where he tried to use as many measurements of various lenses, and both time delays plus modeling of this guy. Kachanik and I think other people did this sort of thing where they tried to model what they thought the dark matter would look like, and use what pops out of the lensing from that on a simple thing in the background, like a QSO, to derive cosmology parameters. That just
yeah. I mean, I imagine, I haven't something specifically, but I imagine like there might be a huge inertia, like what you assume for like mass profiles of the galaxies in those situations. That might be it. So here, maybe like, you have these kind of like, if you put the subhalo right on the critical curve, right, it's pretty kind of spectacular at some level, right? You really distort the critical curve in this case. So I think like you can, in this game, like you said, even though it's kind of like, being hashed out right now, it's like you can really like, it's pretty obvious that there's something there. So I think in some level you can kind of have this point for you. Trying to find these things, and in fact, I think the only ones that have been published right now are these really like super spectacular distortions.
Yeah.
Where they found this distortion of critical curve.
Yeah, I mean, what Kachanik did with quasars, it's really, you just got point sources. So with only like 10 quasars, for example, you're not going to get really strong constraints. But what they found, I think what you're thinking of is they found that the perturbations to the quasar fluxes that you get, it's actually in excess of what you expect from CDM. So it's like you're getting too much substructure.
Yeah.
And part of the reason I think what people are finding is that there's a lot of interlopers in between the lens and us, and that was having a bigger effect than we thought.
Yeah, I mean that's the quasar variability timing. So there's also the modeling of, well, here I've got 4 images, and they have a ratio of brightnesses,
right?
And that you could use to constrain what the mass profile of the lens looks like.
Yeah, right.
And if you do that, various cosmology parameters kind of come into that modeling, and you get Hubble constants of 50, for example.
Right.
That probably is not right.
Yeah,
but the modeling of lenses has improved a lot since then, right? If you look
Yeah,
at the
maybe
Hubble
that's
cow results, they're much more.
for the Hubble lens constant, it's getting competitive. It's the latest thing that came out just a couple of months ago for quasar time delays. They got the Hubble constant within like 3%.
And it's blinded, okay, so they don't know what they're getting until they.
You were talking about the tidal stripping of the subhalo, but for Vmax, I mean that should be relatively insensitive, right, to stripping,
For Vmax.
or circular velocity of the subhalo. And I thought that was part of the reason why everybody always makes these plots of circular velocity or Vmax in a subhalo rather than total halo mass, like the plot you showed at the very beginning.
The, which one?
Where you're just showing the circular
Oh,
velocity
yes. Which of the
function.
I
Vmax?
think he's asking it's Vmax robust and tidal stripping.
Right.
He thinks
Not
it's
as
also.
No, I mean,
Yeah.
you can always get close enough so that you strip it more than that, but I think that once you start stripping beyond Vmax, you're getting to a point where it would just disrupt the subhalo entirely.
Yeah.
I mean, that's what they see in simulations.
But I just mean, in the last few slides, you made a big deal about how the projected separation that you assume for your subhalo, if it's exactly in the lens plane or if it's 100 kiloparsecs out, how that messes up your estimate for the total mass of the subhalo. But that won't mess up the estimate for the circular velocity of the subhalo, so.
No,
So-
but that's not something that we can really get. From the lens, we can't really get Vmax directly.
But if you're assuming a profile for the subhalo,
You can infer.
then, I mean, that's a parameter that you could fit, just like the total mass of the subhalo is, right?
That's true, yeah. But it's still true that if they got close enough, I mean, if it's within a few kpc of the center of the host, they could disrupt it.
Yeah, sure.
So I have a question, actually. I guess this all people, take me back to your last few bullet points.
Mhm.
So, you showed that there's some characteristic mass, you're calling it effective lensing mass that gets constrained by these observations.
Right.
There's probably a bunch of parameters to depends on. So can you make can you go to simulations? Because I think the thing we're missing here is if simulations, can they predict a mass function of, effective lensing masses of subhalos? So that you can actually so when you guys 15 years from now, when you have a mass function of a bunch of lenses,
Right.
you can actually, that's the thing that's the thing you measure. So we tailor the theory to compare to that thing.
Yeah.
Is it possible to get that thing out of simulations?
I don't know. It makes it harder, definitely,
Okay.
because there's scatter in the concentration of these halos. So if you're looking at how much mass is in some radius, there's going to be scatter. Even if I know my subhalo is 10 to the 9 solar masses, depends on how concentrated it is. So yeah, I don't know.
So I mean, that's something, right?
It'll definitely be harder.
But I mean, you've quantified some scale here that matters the most here.
Right.
In this lensing, this is the thing that you observation do. So it might be interesting to think about working backwards from that.
Right,
And
exactly.
giving out the theory rather than the theorists tend to here's Vmax because that's what my simulation told me.
Exactly.
Right. But I mean,
Yeah, we should do
there's got to be some
full model.
there's got to be some
Yeah, that's definitely something we're thinking about doing.
Anything else? All right, so let's thank Quinn again.